Okay, so it is a pleasure here to host the final installment for this year's EMI Dynamics online seminar series. And it's really a pleasure for me because this is the last seminar that I'm organizing. And we have a very special guest. This is Professor Eduardo Kausel, who is a Chilean-born American engineering scientist, specializing in the fields of soil dynamics, structural dynamics, wave propagation, and engineering mechanics, as many of the colleagues in the EMI Institute surely know. As a brief bio, he joined the MIT faculty in 1978 and remained there as a professor of civil and environmental engineering until transitioning to Professor Emeritus in September of 2017, but has been very active since. He has written well over 200 technical papers and reports in the areas of structural dynamics and earthquake engineering and further fields. It has a book, one of the latest books on advanced structural dynamics came out in 2017. His previous book on fundamental solution in elastodynamics has been referenced several hundred times, probably influenced many of the colleagues in our domain and those who are here in the audience. And he has received a number of honors and accolades as part of his service as a faculty and as in our domain, including the Humboldt Prize from the German government in 2000, the 2001 MIT CEE Award for conspicuously effective teaching, which is a very important recognition as well. And in 2015, he was elected a corresponding member of the Chilean Academy of Engineering. And of course, he's also a fellow and life member of the American Society of Civil Engineers, amongst further other honors and awards. With this, I would like to give the floor over to Professor Kausel, who can share his screen. And he would...
Okay, I'm going to share. Well, I'm going to share the screen. Well, I can start sharing right away now.
Yes. And let me just say that you will be discussing classical dynamics problems exhibiting surprising characteristics, as is the title of the talk.
Yeah,
so the
make it big.
Yeah.
All right. Am I on now?
Yes, looks very good. So the
Okay.
floor is...
Thank you. Good morning, good afternoon, whatever. It depends where you are. From California to Europe, it's different time of the day. It's a great pleasure to be with you. It's also a great honor to have been elected the last speaker of the the Dynamics Committee of the Engineering Mechanics Institute, and of which I've been a member for a good number of years. And so I'm very happy to have the last word, at least this year. You know, those of you who know me, you know that I can talk about engineering problems. And in fact, those of you who were in Zurich attending my seminar, it was about the earthquake in Turkey. So I can talk about real engineering problems. But since retirement, I focus mostly on fundamental science, on basically curiosity-driven research for which you only need a computer, a piece of paper, and pencil. And I've been wondering more and more about problems as to the why of problems. Why is it that things are the way they are? I mean, is this going to solve, if you were doing this seminar, some of you, in the audience, you would be talking about new materials, the bridge that is twice as long as all the other bridges, or tall buildings, or in other words, you would be talking about real engineering, I mean, problem-oriented research. Whereas I'm not going to give excuses, but I'm going to be talking about now 3 problems in fundamental science and engineering science. Things that I was wondering, why is it the way it is? And it turns out that I discovered certain things that I will share with you. I have more of these, but with 3, I have plenty to talk to you for an hour or so. All right, let me begin then. I'm going to be talking about basically 3 problems. First, the normal modes, the classical normal modes that all of you in structural dynamics know about. And I'm going to show to you that the normal modes normalized with respect to the mass matrix is already built from the very start into the pair of matrices K and M, into the stiffness matrix and the mass matrix M. It's not at all obvious, but it is very peculiar indeed. that these the normal modes are an intrinsic property of the eigenvalue problem for structural dynamics. Then I'm going to be talking about loads traveling over viscous and lossy media. It could be a beam on an elastic foundation. It could be a load moving over a layered half space, whatever. The important thing here is that the load travels, it's a vertical load traveling horizontally, and as it moves and in the steady state condition, it deforms the ground, and as the ground deforms, it dissipates energy. And the question is, where does that energy come from? Then finally, I'm going to talk about discrete media finite elements, and basically the fact that they, no matter how refined the model is, they're never a perfect replacement for the continuum they model. However, there exists one notable exception that contradicts this statement, and therefore it contradicts the so-called representation theorems, and which are these sacrosanct theorems and elastodynamics. So the question is, how is it even possible that that could be so? So I'm going to make it all of these topics relatively brief, because I would like to allow some time for you to ask questions if you would like to. So let me begin first with the very first one here. And Eleni, you're occupying part of my screen here. I'm going to move it to the side. Okay. If you were to teach structural dynamics, oops, there's some, we move one more too many. Where is it? Why am I page 2? Oh, there we are. Okay, the page down. Not, what's going on here? It's not responding to my...
You may need to click on your screen again.
It's not responding. Oh.
And now click once more.
Let's see. No, it's not responding. Where do I click? That's a question.
On the screen.
No, I was pressing the keyboard, and it's not responding to that.
Now it did. Okay.
Well, all right. The classical modes. Classical modes, if you teach a course in structural dynamics, you know that it's one of the very first things that you will be teaching. And you have you are very well familiar with the expression in the box there, K phi equals omega square m phi, which implies, by the way, you multiply from the right-hand side by any constant alpha, doesn't matter what it is, and then you join alpha with phi, and you redefine as another phi or some psi, whatever, you give it any name that you like, and the eigenvalue problem looks the same, and where alpha is any scalar. And this seems to imply that psi equals alpha phi, J is the index that runs from 1 to n, the number of degrees of freedom, that remains undefined. It is then customary to normalize the eigenvector so that the product of phi transpose k phi, or psi in this case, which is equal to omega square phi transpose m phi equals omega square. In other words, that the modal mass on the right-hand side, mu j equals phi transpose m phi is equal to 1. Now, this is simply achieved by taking alpha to be the square root of that reciprocal mu, of the reciprocal, and the square root of the reciprocal of mu. In that case, phi transpose k phi will be the eigenvalue squared, and phi transpose m phi will be diagonal matrix, identity matrix. And in that case, the psi matrix is said to be normalized. And now, this is very well known to all of you, and this is a very common operation done routinely in dynamics and most programs also that work, for example, in MATLAB, they do normalize the modes in this way. Now, this would suggest to you that the modes really are only defined up to they only define a direction in space, in the n-dimensional space, but that the length of the eigenvectors is not properly defined until you normalize them, or you do something with them. You can scale up any vector up and down, and that doesn't change at all the satisfaction of the eigenvalue problem. And therefore, it would be natural to think that normalization is something completely separate from the eigenvalue problem. But actually, that's not the case. As I will show you, well, we have, the very well known orthogonality conditions. And I can see here that some of my fonts got changed. They're not supposed to, but they got changed. Phi transpose k phi is that k there in the middle is supposed to be slightly different. It's an open face, but it isn't. It's the modal stiffness, and P transpose M phi is the diagonal modal mass. And these orthogonality conditions, if you express K in terms of the modes, you would have K equals phi minus transpose. Oops, why did it go? Why did it go up one? Oh, I touched the touchpad. That's why. That you can express K in terms of the modes and the mass matrix in terms of the modes, and therefore, and you are guaranteed that you can do that because the modal set is not degenerate; it spans a full n-dimensional space, and therefore you can express K and M in terms of the mode. Now consider the transfer functions matrix. K minus lambda M, where lambda is any scalar that you like. The reciprocal of that, if you wish, K minus lambda M is the dynamic stiffness matrix, and you take the inverse and you get the flexibility matrix or transfer functions matrix. And let's look at that expression and express it in terms of the normal modes phi, which the normal modes phi are not yet scaled in any way. They are not normalized. And also the eigenvalues lambda, omega, lambda j, omega squared j. And in that case, it simplifies to the expression you have below, h equals to whatever. But let's look at where it says look minus scaling. H, the elements of the transfer functions matrix, of the flexibility matrix, on the right, they are expressed in terms of the scalar lambda, arbitrary scalar lambda, that we chose out of the blue, and then the eigenvalues lambda j, or omega j squared if you prefer, and then most importantly you have psi transpose, and these are the normalized modes. So by the time we do the inverse to get the transfer function matrix, we already have normalized modes that we have never normalized before. We then never bothered in doing a normalization, but that expression is already in terms of normalized modes. So it begins suggesting that normalized modes are indeed built into the stiffness and mass matrices. So now, if you do, and this is a little bit mathematical, I make no apologies for that. If you do contour integration on the element here of the transfer matrix, H alpha beta are 2 degree, rho alpha column beta identifies one element of the transfer function matrix, and which is this expression here on the right. And it turns out that because this is an inverse matrix, it can also be expressed in terms of cofactor this comes from linear algebra, divided by the determinant of the determinant of the matrix. And then if you take this expression here at the top and do integration on some arbitrary contour, and in fact one contour that envelopes all of the poles, then you get the expression here at the very bottom, where the integral produces a summation over all the modes. And finally, if in fact here you have it also again, and then you evaluate the residues in this expression here using contour integration. And finally, if I, instead of enveloping all of the mode, if I choose a contour that only surrounds one mode, one pole, and therefore this summation here breaks down into just one element here. So this is true at the level of each mode. Oops, this is not doing what I want. There we are. It is, we have that the product of these two modal components, normalized components, equals the cofactor divided by the derivative evaluated at the pole, at the frequency of the mode. And in particular, if you choose alpha equals beta, in other words, the same row and the same column, that's a diagonal element, you can then compute phi alpha for the mode J as this expression that I have here at the bottom. And of course, there's a sign problem, the plus or minus, you choose it any way you like. As long as you are consistent, and from that point on, you compute all the other components properly, there is no problem with that. So finally, and here I skip all the steps, I have a paper where all of this is detailed, But using well-known expressions in linear algebra about cofactors and determinants, we can ultimately infer that the phi alpha j is expressed entirely, what we have here in this box, in terms of properties of the matrices M, and also K in the sense because the lambdas here depend, these are the eigenvalues, they do depend on the modes. So I have here an expression which comes from linear algebra that demonstrate that the normalized modes depend entirely on K and M, where K is the stiffness matrix and M is the mass matrix. And this was not obvious at all from the beginning, but it has also some important and interesting theoretical consequence. For example, you can determine just one mode, any mode, and a normalized, you can completely establish the normal direction and the normalized mode, and without reference to any other mode. On the other hand, if you were to use the classical, for example, inverse iteration shaped by Rayleigh quotient, you will get a mode, but I mean, other than the direction, that will not tell you anything about the other modes and which directions there might be, except of course that they need to satisfy orthogonality conditions. But it tells you nothing about the other modes. Whereas this one here, you can go straight into computing the modes, the normalized modes. Now, in conclusion, the normalized modes are not just scale versions of the unnormalized modes obtained by numerical means, but they're an intrinsic property of the eigenvalue problem. And I consulted this after I had written the paper and I had the draft. I consulted that with my very prestigious colleague, Gilbert Strang in mathematics at MIT, who has written several books on linear algebra and also has been teaching eigenvalue problems and linear algebra for many years. And he was not aware of it. And he says, yes. And in fact, he made aware my paper to some other mathematicians, as a result of which it got quoted also in mathematics journals. All right. One last slide connected to this, and this is going to be a little obscure because here, well, actually, not the last slide. It's modal strain. You can express the modal strains and the modal kinetic energy in terms here of the modes, the normalized modes, and you find very simple expression where the Q's here are the modal response functions, Q of function of time, and the kinetic energy then becomes a very simple expression of these modal response functions. Now, my last slide on this is on the eigenvalue problem is something that you might say this looks peculiar because this is not a structure. This is not a structure that has classical modes. I'm talking here of a layered medium that has the so-called love modes, for example. And it turns out that those are also modes. I mean, what happens is, unlike the structure where you get a standing wave, and the standing wave produce what we call modes. In the case of unbounded media, open media, these waves are also standing waves, but they propagate forever in some specific direction. Now, the reason I mentioned this, and the only reason for including the slides, is that when you do modal superposition, like I have here at the top, to get the displacement at some point in terms of the modes, the love modes, and this is an exponential factor that controls the propagation in the x direction, and this is a time modulating factor. When you do that, you normally use the classical modes that are obtained from in seismology and also in elastodynamics. But there is the possibility there, and which has been used by some people, where they choose modes that are unphysical. They do violate the boundary conditions at infinity, the radiation condition, the boundedness condition. And these modes are non-physical because in fact, they grow to infinity at an infinite depth. And if they're infinite, you cannot normalize them. And in fact, the energy in each mode is infinite. And yet, you can express in a very similar way that we have up there. You can use these unphysical modes in order to express displacement at the finite locations where the displacements are not infinite. Now, how this is so, I don't have time to explain, but it is indeed, it is indeed possible. And this is possible only because the modes, the love modes that we so obtain are already not, I mean, they do not satisfy this condition, but they're guaranteed to be normalized in some generalized way. So I find it then peculiar. In fact, this is how I got started in this problem, because I knew that seismologists and geophysicists, they never solve eigenvalue problems. They look for poles or singularities in their equations, whereas the structural engineer actually does solve eigenvalue problems. And so I was trying to understand and bridging the gap between the seismologists and the engineers. All right, this takes me to my second problem, which has to do with traveling loads. It could be a load like we have here at the top figure, a vertical load traveling with constant speed over a beam, and the beam rests on an elastic foundation or a viscoelastic foundation. But it doesn't have, the beam could also be resting on a viscoelastic half space or a layered half space, or in fact, no beam, and the load travels directly over in the half space or even within the half space. Now, it turns out that this problem has been well known for many, many years, and solutions exist now for a good number of years. In fact, the first elementary solutions began being developed in the 19th century in connection mostly with trains, and trains at the time moved very slowly, and dynamic effects were not terribly important. But in which case, approximate solutions based on beam and elastic foundations were sufficient. But later on, the rigorous solution was developed about World War II or so, and this solution became available that predicted the exact response, steady-state response of the beam on this viscoelastic, on the elastic foundation at the time. At the time, it was elastic. And it was found that there is a steady-state condition where you have a basin, the load travels with the basin, everything travels together from left to right at a constant velocity, and from the point of view of an observer that goes with the load, nothing changes. I mean, it looks like a static problem. The basin moves together with you, and the implication is that the energy, the deformation energy in the ground, which is produced by the load, travels in tandem with the load. Everything moves together as a unit from left to right. In other words, we get an expression for the displacement. Here's the vertical displacement, which x minus vt, this is the x is the horizontal coordinate, v is the velocity, t is time, z is the depth, and zeta is the damping. Oops, zeta is the damping. This, in the original solution that goes back to the 1940s or so, zeta was 0. It was an undamped solution. And the deformed configuration here, the basin was symmetric relative to the load. The load occupied the lowest point, and the basin was symmetric relative to the load. Now, by the time that you add damping to the system and you solve the equations of motion, the linear equations of motion for this, you still find the basin, you still find a steady-state solution. I mean, that's not a problem. And peculiarly, for many decades, actually, these solutions have been known. I mean, there is the solution of Kenny that goes back to the 1950s, and it has been published. Everybody uses it, mostly for wave propagation, for trains and fast and loads that move over the ground. And nobody in these 10 or, I mean, in this half a century or so, as far as I can, as I was able to determine, I looked left and right and I couldn't find any reference. Nobody seemed to worry about the fact that as the load travels and you deform this basin, the ground deforms, and as the ground deforms, it dissipates energy, steadily dissipates energy. And how can that be possible? I mean, the load, I mean, if I look at here at this vertical load, and by the way, when you have damping, the basin is no longer symmetric. There is more displacement behind the load than ahead of the load. It rises rapidly ahead. And the important thing is that here the load no longer occupies the lowest position in the basin, but it is slightly ahead. But other than that detail, the characteristics of this problem are extremely similar to those of the classical undone problem. However, nobody worry about the fact that this is dissipating energy, and if this load at this point here, I mean, if this moves from left to right, this has no vertical displacement. The load does not move vertically down or up. And if it doesn't move vertically down or up, it does not provide energy, does not supply energy, doesn't dissipate energy, anything. And in fact, since the load travels parallel, perpendicular to itself, the load is vertical, the motion is horizontal. If you look at how much energy gets produced there is zero. There is no any. In other words, my traveling load is moving. The basin, the soil, the elastic foundation, whatever it is dissipating energy. And this is, logic says that this cannot be. It's simply, so the first thing I did was figure out if there was an error in the equations of motion. I derived the equation of motion for the beam and also looked at shear beams and other things. And I looked at the transient. What happens if I start at a given time t0 and at a given position x0, and how does the solution evolve from there? And it turns out that solution evolves very quickly from the initial conditions. The transients that exist there dissipate very quickly, and very rapidly you end up in a steady state, the classical steady state solution. So I concluded that the solutions to these equations, they were correct. They had no mistake, and yet, I said, this cannot possibly be true. It cannot be that the system dissipates energy and there is no source compensating for that energy. So I looked left and right, and then, of course, it sort of got illuminated as to why this is so. After initial transit is dissipated, the beam vertical deflection attains a steady state that travels in tandem with the load even when the system is down. The point directly underneath the load does not move or oscillate vertically. Therefore, it does not perform or supply any work. Since the load does not move vertically, it can be replaced by a mass because there is no inertia then, by a mass whose weight equals the load, and that is a classical train, that we have a train with mass instead of having a load. And nothing changes. Everything remains exactly the same as before. And the elastic energy associated with the deformation of the subgrade travels with and at the same speed as the load. That energy is constant because the deflected shape is constant, and therefore it does not exhibit any fluctuations, any changes in time. But as the foundation deforms, it steadily dissipates energy. And so the question is, where does that energy come from? Well, you can ignore here, the equations look complicated, but there's nothing mysterious here. The first is nothing but the differential equation for the beam here with mass on the viscoelastic foundation. And this is the traveling load. And this is not very difficult to solve. This is the solution, the two solutions. R is for the right, L is for the left. So C is the distance from the position of the load forward, and C less than 0 is to the left of the load. And these coefficients are defined as being here, and delta and Z are parameters that depend on the beam, the physical parameters of the beam, and also C on the damping, the measure of damping. And M here is the Mach number. The Mach number being the ratio of the velocity of travel divided by what's called the critical velocity, which I don't have time to explain, but it is a critical velocity in the absence of damping is some kind of a resonant condition, which exists when the group velocity and the phase velocity are equal. Anyway, this solution is not difficult to establish. And once you have this solution, you can go and compute the instantaneous power dissipation in the elastic foundation, which here is an integral on the left side, behind the load, and then on the right side, ahead of the load, and you do this and you end up, I didn't do it by hand because the integrals themselves can be complicated, so I use MATLAB, and I obtain this expression here that look quite relatively simple. And top of the load P, the critical is the critical velocity, rho is the mass density, I is the cross section, and the rest are parameters, including the Mach number. Now, I said in order to introduce a source of energy, I need to introduce a horizontal component of the load. And I'm going to be assuming that there is a very small horizontal component, small in the sense that it is much, much smaller than the load, the traveling load. And I needed to say that or to imagine that because it is, I mean, I need, in order for my solution, my linear solution to remain valid, remember this linear solution is always solved in the undeformed configuration. If I produce small perturbations, the linear solution remains still valid, and there is no problem. So, assuming small, oops, I move here. I'd like to move here, and it does something that I don't want. Well, and this horizontal component, where is it going? This is not so simple actually. I'm trying to here. The source, the supply of energy is the horizontal component h times the velocity, and equating that to the power dissipated to the expression near the top, you find that the ratio of h over p, this is disgusting. The ratio of h over p is this very simple expression here. And then in addition to that, if you make some very simple computations for a physical medium, you conclude that this ratio gamma, which is some kind of a strain, is on the order of 10 to the minus 3, a very small number, which means that h indeed is a lot less than p. It's a very small number, and therefore the linear solution remains valid. Now, it turns out, therefore, that when you do get, when the system does have damping, that forces the load to recline back a little bit so that it acquires a very small horizontal component. And it is that horizontal component that provides the energy. But then you probably, I mean, if you are familiar with this type of problems, you would say, hey, wait a minute. The horizontal component acts in the axial direction of the beam. How is it that it provides energy in bending? I mean, in bending the beam, and that gets transferred to the subgrade. Well, yes, that's true. That is true. But then remember that the linear solution is based on formulating the equilibrium in the undeformed configuration. So I said, what happens if I now do the equilibrium in the deformed configuration, and I take into account the fact that the beam rotated and displaced? Well, and then if I look elementary analysis, how much the beam rotates at a given section here, I'm obviously grossly exaggerating this thing here, but I'm looking at the rotation of the middle line, and it is given by this expression up there, here, the tangent. And it turns out that expression is identical to the rotation of the load by the time you compute the horizontal and vertical components. So that's the reason. So the load rotates in such a way that it remains perpendicular to the middle line, to the neutral axis. And if you formulate now the equilibrium, the true equilibrium and the deformed configuration, you're still satisfying the beam equations, the equilibrium and the beam equation. So the linear solution remains valid, and yes, you're still providing energy in bending to the beam when you account for the fact that this is done in the deformed configuration and not in the undeformed configuration. Well, however, there is a caveat. The solution that I just showed you, or that I sketched for you actually, for an inclined load depended on the assumption that the horizontal component of the load is small, and therefore that the rotation is small. And this allowed the standard solution, the linear solution, to remain valid. However, loads must recline back for a solution to exist. That is also true. And a detailed examination of the damn case, the formulas that I showed very briefly in my previous slides, show that at the critical velocity, when resonance effects become manifest, the rotation may not be small at all. That is, h can be much bigger than p. In that case, the entire interpretation that I just described to you breaks down. It's no longer true. This means either that the linear solution does not exist at the critical speed, or more likely that the solution does exist, but that solution is not linear. I do not know the answer to that, whether there is no solution or there is a solution that is non-linear. However, for those of you who are in engineering and are worrying about trains that move fast, you use safety criteria like here what is it? There we are. Where is my caveat? There. At the very bottom, the very last row, it says M equals V over V critical less than 2/3. This may not be conservative enough because the solution at the critical speed is not valid anymore. Simply, it's not true. It may not exist. You would have quasi-resonances way before the critical speed. Therefore, if I were to make an engineering suggestion from here, I would change this 2/3 perhaps into 1/2, and make sure that you're far away from the condition where the solution breaks down, etc. Okay, so this is my second topic, and I still have time for my third. Now, this I'm going to make it also very brief. I would like to give you time to ask questions. If you know that if you have a body, it doesn't matter what the body is, the material doesn't have to be homogeneous. It has you have loads applied to the system, and we'll assume these loads are applied to the surface of the body. And the shape of the body can be anything you like. And this thing at the bottom here, it's a symbol for boundary conditions of some kind. You restrain the system such that it doesn't move, or it moves in prescribed ways. Now, usually most of these problems are so complicated that you don't have exact solutions for them. And therefore they say, oh, no problem. We can use finite elements, we can use finite differences or whatever, discrete methods. And we change the continuous body into a discrete body that can be solved using these numerical methods. And of course, now you say, well, I need to have an accurate solution, so I'm going to take a lot of elements. And in fact, I've seen finite element models that have not only thousands, but even millions of degrees of freedom. For example, the models that they use to model the airplane colliding against the Twin Towers. There was a company that did those analysis, and the model for the plane had millions of degrees of freedom. Actually. Anyway, you use enough degrees of freedom, you say, my discrete system now reproduces pretty much the continuous system. Actually, that's not true. That's not exactly true, because there will always be a limit which depends on the size of these elements, where waves cannot propagate anymore. And so the answer to this question as to whether the discrete system can reproduce the continuous system, the answer is no. However, there is one most notable exception that can be distilled from the work done by Murthy Godati at North Carolina State University. He has a series of very obscure and very highly mathematical papers on silent boundaries. And in these papers do not mention what I'm going to be mentioning, but they're already contained there. And I suppose that Professor Godati knew about that, but didn't really worry too much about it. But anyway, I worried sufficiently that I wrote a brief paper. I sent it to Godati and asked for his permission to publish it. He says, by all means, do. This is certainly very important. It distills basically some of these notions that I will describe here. Well, let's assume that we have a homogeneous elastic half space, and it is subjected to forces applied on the surface that have any spatial variations and any temporal variations. It doesn't matter really. You could have spatial variations describing very short waves, and or temporal variations where the frequencies of those waves can be very high. Now, this can be solved exactly by various means. One of them is the impedance matrix method, transfer matrix method. There are many methods. And all of these are based on changing the load in time to load in the frequency space domain. Okay, here's a wave number. It's the reciprocal of wavelength, and omega is the frequency. Then you use operational methods to change the equations of motion. You find that in that frequency of space domain, wave number domain, these loads here are expressed in terms of an impedance matrix and the displacements. This can be solved numerically on the computer, and then and you find a solution. In principle, if this product were simple enough, and there are some simple cases that you can solve by hand and do an exact solution using contour integrations. But in most cases, you need still a computer to find that exact solution. On the other hand, if that very same continuous problem remains exactly the same, if I introduce an artificial layer, remember this is a homogeneous half space, an artificial layer here that has the same properties as the half space below, that is still the same problem as before. Yes, the equations change now. You have an impedance matrix for the layer, an impedance for the half space, but the problem is the same, and you can still get the exact solution not only at the surface, but anywhere you like, also in the interior of the system. And this is the continuous exact solution. And what Guddati discovered, or actually didn't discover, he has it there in his paper, is that there is a discrete solution that from the surface, only from the surface, from the green line that you see at the top on the right, the green line, from that surface, the solution is exactly the same as these two other ones on the left and the middle as the continuous solution. This discrete solution is basically based on the thin layer method, where you discretize the soil into thin layers in the finite element sense. Basically, you introduce an expansion for the displacements in the vertical direction. And this becomes, it's a quasi-finite element. It's in the sense it's a finite element vertically, but it's continuous horizontally. And that allows for some very neat and beautiful solutions, actually. But the fact is that this figure here on the right, this one here, consists of discrete layers. And therefore, it cannot transmit all of the waves vertically. In fact, waves that are shorter than the thickness of the layers or a few, they cannot be transmitted. And yet, as I will show in an exact form, the solution at the surface is exactly the same as the other one. And how can that be possible? So we have here the solution. Again, the P of omega is in the frequency wave number domain. Z is exact. In this case, I'm looking at the simple case of SH, acoustic impedance of the half space. And then this is the formal solution using inverse Fourier transforms, where the numerator, this is the source here. This is the Fourier, the kernel of the Fourier transform. And this is here's the flexibility, actually the reciprocal of the stiffness, the impedance. And that gives you the exact solution. Now, in the second case, where I added, you remember the figure in the middle, I added in a fictitious layer, an additional layer. That one is characterized by an exact impedance matrix like the one I have here. P1 is the load supplied at the top. 0 is the fictitious interface that there are no loads there. This is the impedance matrix of the layer. This is impedance of the half space. Oops. Of the half space. And then you solve here for the displacements, and there you are. Now, on the other hand, if you, instead of using the exact impedance, which is when the matrix I have here in the middle, and I don't dare move where it is, there. This is the exact impedance. If I replace this exact impedance by the discrete impedance of the thin layer method using the central point integration, as you can see, this thing here looks very different from this thing here. And the discrete impedance And by the way, here K is embedded in transcendental functions, whereas here K, the wave number, is explicit and the same as the frequency. Now, when I can express these elements here of the discrete impedance as A, B, B, A, and I introduce it into my solution, and I solve this, remarkably, I find that it equals to, oops, I need to go back. It's equal to the impedance of the half space times the displacement at the surface. Therefore, miraculously, we recover the exact impedance at the surface, no matter how thick the layer, the thin layer, the TLM layer is. Maybe one thick element, or it could be one thin element, it doesn't matter. Now, since this is true for one element that has any thickness that I like, it by recursion is also going to be true for two such layers. And if I continue the recursion, I can have any number of layers, and it is still going to be true. It's still going to be true. So I can have now a deep, profound system of layers that are based on the thin layer method, and the solution at the surface is going to be exactly the same as before, as the exact solution. Now, that I tell you, if somebody had told me that would be true before, I would have said impossible. It cannot be, because waves cannot penetrate the ground in the way that they do when you have a continuous system. But in this case, it happened to be true. Now, there is something else that is also quite remarkable. The fact that this, if you look here at this expression for the discrete impedance, it is a function of H, and H here. It is a function, it is a function of the thickness of the thin layer. But by the time that you are through, by the time that you do this operation here and you arrive at ZH, which is the impedance of the half space, the exact impedance of the half space, which is what we have up here, this expression in the box, there is no H there. There is no H. And if there is no H, it means that the thickness of the thin layer doesn't matter. It can be as thick as you like. And most remarkable, since it doesn't matter, you can even make it complex. It doesn't have to be real. You can take a complex thickness, and this result is still going to be true. So the amazing implication is that since the thickness of the condensed layer disappears, this means that TLM could be as thick or thin as we wished. That because this is true for one layer of elastic aspect, is true by recursion for any number of layers of all of different thicknesses. For the same reason, we could make complex numbers, and the same results will be obtained at the surface of the system, at the surface. After stacking a few TLM layers with complex thicknesses, the system will start behaving internally as something called a perfectly matched layer, which is some kind of an absorbing device. Let me make a parenthesis here. I said the solution at the surface is going to be exactly the same. However, the solution internally in the discrete layers is not going to be the same. And we know that because since the system is discrete, there are certain waves that cannot propagate there. However, by the time they make the thicknesses of the discrete layers to be complex numbers, it behaves like a perfectly matched layer, in which case a stack of those thin layers becomes an absorbing system. And in fact, if you take it thick enough, there will be no waves arriving at the bottom of that system. In that case, we have arrived at the ultimate absorbing boundary. We start with a system defined entirely in terms of thin layers, of discrete layers. You take, say 10, 20, 30 of those, make the thicknesses complex, and presto, you get an exact hash space, at least as seen from the surface. That is absolutely remarkable. But what is even more remarkable, what I showed here for SH layers is also true for the much more complicated case of plane SVP case, where there are two components of motion at every layer, at every point. And since three-dimensional loads can be obtained as the superposition of SH and SVP, I mean, the two plane strain cases can be superimposed to get axisymmetric loads with any variations in the azimuth. It means that what I just told you about this perfect boundary is also true in 3 dimensions. I mean, I can construct with the thin layer method using the matrices of Guidati. I can simulate exactly a half space with discrete methods, and that is truly remarkable. So the profound consequences is that we have here one example that, at least from its outer surface, behaves in exactly the same fashion as the continuous system that it replaces. And there is, if you were to make a test from the surface, any test that you like, I mean, looking at recordings in space-time, there is no load combination, no matter how rapidly it changes in space and time, that you could tell you that what's underneath there is not the continuous system that you think you have, but that you have a discrete system. And that, I mean, to me, this is truly amazing, actually. Now, because this is true, it denies and falsifies the belief, or actually the theorem, that the representation theorems are strictly valid. These are the sacrosanct representation theorems that are used in the boundary element method and many other methods. And when you do synthetic seismograms and seismology, you also use representation theorems. And this would suggest that these representation theorems are somehow fail in this case, because this is clearly a failure of those representation theorems. Now, the reason why this is true in this case is because my system is open. The body in question is unbounded, is surrounded by a surface that is infinitely large, and therefore the representation theorems which were developed and proven in elasticity and elastodynamics for finite bodies do not necessarily apply to infinite bodies. And so here you have one body, at least, that is going to be violating this principle. In consequence, here you have a case where there is at least one system, a discrete system, that at least on the surface of that system behaves exactly like a continuous system. And if somebody had told me a year ago or two that this is possible, actually more than that, because I published this longer ago, if somebody had told me that this is possible, I would have said with great confidence, this is totally impossible, actually. But I proved myself wrong, actually, and this was pretty good. All right. So in summary, normalized modes are an intrinsic property of eigenvalue problem, and not just a convenient scaling. In the case of moving loads traveling over dissipative medium, the dissipation of energy in the lossy medium requires the moving load to lean back in order to provide basically a component that delivers the energy. And this will be true only as long as that small horizontal component is small enough that you can still satisfy the equilibrium and the deformed configuration. However, as you approach the critical speed, whatever that is, I don't have time to explain that, the classical linear solution will break down and will cease to be valid. So beware of those classical solutions near the critical speed. And then finally, I have shown you that there exists at least one system involving elastic open solid for which the continuous and discrete solutions on the envelope, the surface of that solid, are indistinguishable at all frequencies and at all wavelengths. All right, this is what I had to say, and I have here some bibliography, and I'll be happy to answer questions. We still have 5 minutes. Thank you.
Thank you very much for this very nice presentation. And I see that there's already even a raised hand. So perhaps I give the floor directly to Arslan. Yes, go ahead.
Thank you. And it's good to see you, Eduardo. As you were talking about normalization being an intrinsic property of dynamical systems, I was trying to see if it can be generalized to some classical problems of dynamics, such as mass degradation or ablation systems, a rocket, if you imagine, ascending fast and losing a lot of mass, and you look at it's a linear elastic problem, and you try to find a P wave in the skin of the rocket. Does the conclusion hold for these cases?
I'm not familiar with the problem you're describing, but I can tell you one thing. the properties I described, the remarkable property that I described, is true for the specific eigenvalue problem that I was considering, where the linear eigenvalue problem, where K is positive semi-definite or positive definite, and the mass matrix is positive definite. It's symmetric matrices. If you have other types of matrices, whatever I said is no longer true.
You answered my question.
Good.
There is actually one more question which is in the chat, but in case Armin could unmute, you can actually ask the question yourself.
Sorry, I have a question.
Jose,
Yes,
you.
Yes.
Go ahead.
Yeah. And now the camera is on operating well.
Yeah.
As you can imagine, Eduardo, my question is about the critical velocity.
Yes.
If I haven't misunderstood you, you have said that the equations, the linear equations, doesn't work well in the vicinity of the critical speed, and you have mentioned, let's say, a safety factor of 2/3, and if we put it in inverse 1.5.
Yeah.
Do you have any criteria to establish that safety factor? I mean, perhaps the increase of the movement relative to the static case,
I'll tell you right away. I don't have the answer to that, because in order to answer that, I would need, me or somebody else, would need to see at what speed the linear solution begins to break down. In other words, you would have to see, I mean, for what value of the Mach number of the ratio of the travel velocity divided by the critical velocity, at what ratio the H becomes sufficiently large that the equilibrium and the deformed configuration is no longer, I mean, at least built into the linear solution, is no longer valid. And therefore, then you need to do something else. What that else is and at what speed that would happen, I don't have a good sense, but I suspect it's going to be relatively close to the critical speed, because if you look at the amplifications, they rise very quickly in the vicinity of the speed. So I suspect it's not going to be terribly different. But that means also that the solutions that Kenny has published in the 1950s, and he also has solutions for the transonic range, I mean, beyond the critical speed. I don't believe those are true. I mean, they may not exist. In fact, the solution may not be linearly, but at least for a, let me rephrase that. It's not going to be true if you have damping. If the system doesn't have damping, sure, then the linear solution remains still valid. But if you if you have damping, then everything breaks down.
Yeah.
And I have good sense. By the way, your camera returned, but you have the light behind you, so your face is still obscure.
Oh, sorry. Now it's better.
Yeah, that's a lot better.
Okay, thank you. Sorry for that. Okay, so thank you for your answer, and congratulations for the presentation.
Okay.
There is again a raised hand by Erdogan. Is that correct? Would you like to add?
I have a few questions, but I want to give others a chance also. But thank you. About the second part of your talk, I was a bit troubled, I should admit, about the introduction of a little horizontal force H at the boundary, and I was wondering, why shouldn't we instead look at an Eulerian formulation of large displacements at the boundary, because that gives you the components that you want, and you don't have to introduce.
No. I mean, in the cases of a beam, look, I mean, a beam is, the reason for studying the beam is because the equations of motion of the beam are relatively simple. When by the time you can also look at layered media, and then the equation becomes far more complicated. When if you look, for example, in fact, don't even look at the layered media, look at the elastic hash space. You have a load traveling over the surface of the hash space. There, the load is perpendicular to the direction of motion, and therefore it cannot supply any energy. The only way you can supply energy is because the ground somehow offers resistance. How does it offer resistance? Well, what happens is that the ground no longer deforms symmetrically relative to the position of the load, but the load is now on a slopy ground. And
Exactly.
the force is basically going uphill. In order
Yes.
to compensate going uphill, it forces to rotate, lean back in order to be able to go up the hill, so to say.
That's
That-
what I meant by a co-rotational formulation, where we are not fixing the coordinate system and we are allowing the rotation to naturally, in a large displacement formulation, account for the displacements.
Well, look, Arzak, that is exactly true. If you do a large displacement formulation, you will be able to solve this problem. And perhaps your next paper will be about that topic, actually, that subject. Now will be, when you have it ready, please send me a copy. I'll be happy to read it.
Thank you.
Yeah.
Allow me to also read the question, unless Armin Dadras would like to unmute. I'm not sure, because he's online, but I'm not sure if you can use your microphone. If not, there is a comment in the chat, and I'll just read it for you. It says, thank you for the excellent presentation. I would like to add a comment regarding the third topic you discussed. In this simulation, we're solving a differential equation. In essence, what we're doing in these simulations is therefore integration. And it is a case within a broader family of mathematical problems that the circumstances under which numerical integration aligns with analytical integration. I'm not sure I transmitted it correctly, but that's what is written. And the mention here is that I think the key to obtaining accurate solutions lies in ensuring that the assumptions made in both types of integration are consistent. If the assumptions contradict each other, such as a change in the geometry of the layers, for example, then discrepancies would arise. I'm not sure I understand part of the question, but maybe it's clear to you.
Actually, yeah, actually the same is true with me, actually.
So
I'm
maybe
not exactly
we
sure.
will leave this there and hope
Well,
that
I
there's
mean,
a
I
clarification.
would agree that in fact, that was my very first problem. If you solve equations of motion based, the classical equations of motion based on linear deformations, and you find that something is absurd, for example, how can it dissipate energy without any source?
Any input of energy.
Something, yeah, without any input.
Yeah.
That obviously, I mean, my instinct says something is wrong. In fact, at the very beginning, I thought that there was something wrong in the equations themselves. That basically, by the time you have dumping, there was something wrong with equations. But after playing around with equations themselves and looking at various possibilities, I realized that no, there's nothing wrong with equations. But I realized that the equations, the linear equations of motion, you formulate the equilibrium in the undeformed configuration. Whereas the horizontal load that you need to supply the energy, it acts in the large deformed configuration. Well, large, yes, large, but they're still small compared to everything else, to the dimensions of the system.
Maybe a question on my end. Or Irfan, would you like to say something? I saw you.
I was just saying, I need to hop off, so I just direct messaged you on that.
Sounds good.
Thanks.
Thank you for making it.
Thanks.
Maybe a question on my end relates to the third problem that you showed, exploits essentially a semi-analytical solution in the spirit of what we would also see, for example, in scaled boundary finite element methods, which try to exploit a discretization only around the boundary, and then an analytical solution within the domain.
Yeah, that's
it is a bit of such a lot. Yeah.
No, you know that scale boundary element method, whatever it's called, it has a very long name.
Yes,
basically it's basically the same as the thin layer method, except that instead
I think so. I didn't realize. I was
formulated in terms of horizontal layers who have cylindrical
instead of radial.
actually cylindrical sectors. But other than that, it is still a finite element.
Yes.
And well, I mean, you know, there in that case, something more dramatic happens, because suppose that you have a sector, and here the boundary is here where the sector almost comes together, and you transmit waves, and this sector is discrete. In other words, and if it is discrete in the azimuth, it means that as the wave propagates, the wave has more difficulty propagating, because the wavelength becomes more comparable to to the size of the
To the
distribution,
critical
as a result of
point,
which
yeah.
the waves will penetrate this medium and eventually they will reflect
Yeah.
back into the system again,
Yeah.
which
Okay.
doesn't happen in the regular thin layer method. But actually, it's basically the thin layer method in a different coordinate system.
This is what I gathered, so now I'm curious and we'll go back. Are there any other questions from the audience? As we're slightly exceeding our nominal duration, but I think if there is a last question, we can afford it. If there is not such a last question, I would like to give the floor back to Eduardo and ask what would you like to leave the audience with after such a very inspiring talk on fundamentals, which I think is where everything begins from.
Well, I mean, these are 3 examples. I have more, but things that are of interest to me. Now, remember, I'm a retired person, so I do not lead the large scale engineering projects with lots of funding and lots of students, doctoral students, to keep them working. So, but that means that I have the time and the means to look at problems that everybody else neglects. And that nobody really worries about those. In fact, if you ask me what is the value of what I just did, I mean, why is it important that, for example, that the modes are normalized,
Naturally scalable.
Yeah, it's part of the system. Well, I would agree with you. It's not terribly important. I mean, you're going to continue doing your mode analysis the way you did before. You're going to normalize the modes the way before. But I thought that from the knowledge point of view, from the curiosity-driven research point of view, it's very important. I mean, you learn, I mean, you tie things, you dot the I's and cross the T's, and you begin learning something new about it. I mean, to make a comparison, if you look at an engineering project, well, and what you can look at the advantages, the economic advantages, we'll have the bridge, etc., to this island, etc. So in other words, you can compute an economic value to some engineering solutions. But if you were to ask you're now at the beach and you're watching a sunset, and there's a beautiful sunset and the environment is very beautiful, and then you say, what is the economic value of that? Well, it doesn't have economic value, but it doesn't mean that there's not values. I mean, there's a beautiful sunset, it's a beautiful environment. And the fact that you could not put a number, a dollar value, and does it mean that you can now change that beach and put buildings there and basically destroy the beauty of that? No, of course not. Well, the same happens with basic science. I mean, there are some nuggets there, some beautiful little pieces that are of interest to me. I have some more actually, and
yeah, I'm sure. Actually,
the problem I have is that I mean, I'm interested in so many things that I don't have the time to write about them. And besides, it's not only in engineering science. I'm also very interested in photography. I've been doing a lot of that, and I love it. And I find that my team. I'm busier now than I was when I was at the faculty at MIT. Actually. I'm busy.
This is an interesting statement, but a very good note to close on because it motivates curiosity and creativity. So I want to thank you very much for offering this seminar. And I want to thank everyone for attending. We will continue in the next year with announcements on our next guest.
Okay.
Thank you very much.
I wish you all a happy new year and all the best for next year. Who knows? We might see you somewhere.
Sounds very good.